You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine. Of course, I was an ordinary person who studied hard. There's no miracle people. It just happens they got interested in this thing, and they learned all this stuff. They're just people. There's no talent, a special miracle ability to understand quantum mechanics or a miracle ability to imagine electromagnetic fields that comes without practice and reading and learning and study. So if you say you take an ordinary person who's willing to devote a great deal of time and study and work and thinking and mathematics and time, then he's become a scientist. The great difference in what goes on in the head when people think they're doing the same thing. And so it struck me, therefore, if that's already true at the most elementary level, that when we learn the mathematics and the Bessel functions and the exponentials and the electric fields and all these things, that the imageries and method by which we're storing it all and the way we think about it could be really, if we could get into each other's heads, entirely different. And in fact, why somebody sometimes has a great deal of difficulty understanding a point which you see as obvious, and vice versa, it may be because it's a little hard to translate what you just said into his particular framework and so on. Now I'm talking like a psychologist, and you know I know nothing about this. Suppose that little things behaved very differently than anything that was big. Anything that you're familiar with, because you see, as the animal evolves and so on, and his brain evolves, it gets used to handling, and the brain is designed for ordinary circumstances. But if the have a mathematical expression, strange as mathematics, I don't understand how it is, but we can write mathematical expressions and calculate what the thing is going to do without actually being able to picture it. It would be something like a computer that you put certain numbers in and you have the formula for at what time the car will arrive at different destinations, and the thing does the arithmetic to figure out what time the car arrives at the different destinations, but cannot picture the car. It's just doing the arithmetic. So we know how to do the arithmetic, but we cannot picture the car. No, it's not 100%, because for certain approximate situations, a certain kind of approximate picture works, that is simply a fog around the nucleus that when you squeeze it, it repels you. It's very good for understanding the stiffness of material. That it's a wave which does this and that is very good for some other phenomenon. All right? So when you're working with certain particular aspects of the behavior of atoms, for instance, when I was talking about temperature and so forth, that they're just little balls is good enough, and it gives a very nice picture of temperature. Is it possible then to develop a familiarity with those things that are not familiar on hand by study, by learning about the properties of atoms and quantum mechanics, by practicing with the equations until it becomes a kind of second nature, just like it's second nature to know that if two balls came toward each other, they'd smash into bits. You don't say the two balls, when they come toward each other, turn blue. You know what they do. So the question is whether you could get to know what things do without better than we do today. You know, as the generations develop, will they invent ways of teaching and ways so that the new people will learn tricky ways of looking at things and be so trained, so well trained, that they won't have our troubles with the atom.